Assalamu alaikum. My name is Hammad and I am from the Department of BS Biotechnology. The topic of my presentation is determination of water hardness by titration method. We'll start off with the basic intro. The method called a complexometric titration is used to find the total calcium and magnesium content of any solution. It can be milk, it can be seawater, or it can be a normal water. The degree of hardness or degree of water hardness is determined by the extent of calcium and magnesium ions present in the water. If they are present in larger extent, the water is more hard. If they are present in lower extent or if they are absent, the water is called soft water. The method uses a very large molecule called EDTA which forms a complex with calcium and magnesium ions. That's why it is called a complexometric titration because complexes are formed in it. The EDTA and the indicator as well form complexes with metal ions. The EDTA is short for ethylene diamine tetraacetic acid. The indicator used in this process is Calmagite. Calmagite is a complexometric indicator used in analytical chemistry to identify the presence of metal ions in the solution. Calmagite will be wine red when it is bound to metal ions, and in non-bound form it will be blue, orange, or red. Hard water. Hard water and process to detect its presence. Hard water contains multiply charged ions as we have discussed. These are calcium and magnesium. There are other heavy metal ions as well, but the ions that are present in the largest quantity are magnesium and calcium ions, which replace sodium and potassium ions in soap and detergent to form precipitates. These precipitates interfere with cleansing action and leave unsightly bathtub rings and scum. In addition, when water containing Ca2 plus, which is the calcium ions, and the SiO3 ions is heated or boiled, calcium carbonate is formed. This is the main component of the scale seen in tea kettles and can cause clogging of pipes and boilers in industrial settings. We do see that white thing in the tea kettles or the pots that we use to boil things. That white substance is calcium carbonate. Now we'll talk about the EDTA. In the determination of water hardness, ethylene diamine tetraacetic acid is used as a titrant that complexes calcium and magnesium ions. Although neither the EDTA titrant nor its calcium and magnesium complexes are colored, the endpoint of the titration can be visually indicated by adding a metallochromatic indicator to the water sample. As we have already discussed that indicator, that is Calmagite. A color change occurs when the indicator goes from its metal ion bound form to the unbound form. We have discussed that as well. It is red. The Calmagite is red when it is in bound form and will be blue, orange, or red when it is in unbound form. This color change signals the endpoint as it takes place when the EDTA, after complexing all of the unbound Ca2 plus and magnesium ions, removes the magnesium ion bound to the indicator. This removal is only possible because EDTA complexes magnesium ion more strongly than the indicator. This demonstration can be used when discussing complex ion formation to emphasize the correlation between success in the competition of different complexing agents for the same metal ion with the values of their respective complex formation constant Kf. The Kf, which is called the complex formation constant, if the value of Kf of a particular compound is high, that means it has a higher affinity or a higher power to form complexes with metal ions. The EDTA has a higher Kf value or the complex formation constant as compared to the indicator that we are using, which is Calmagite. EDTA is widely used in analytical chemistry as it forms strong one-to-one complexes with most metal ions. The process. The neutral acid is tetrapodic acid and is often denoted as H4Y. For calcium and magnesium ions, the complexation reactions with Y4 and corresponding formation constants are given below. Calcium ion reacts with the acid to form calcium acid, form a complex. The Kf value when it bounds with the calcium is 5 multiplied by 10 to the power 10, and when it bounds with the magnesium, the Kf value is 4.90 multiplied by 10 to the power 8. The large magnitude of these formation constants indicate that the above reaction will go to completion if the EDTA is present in its completely deprotonated form Y4 plus. To ensure that titrant in its completely deprotonated form Y4 pH of 12 or greater is necessary. Unfortunately, the precipitation of Ca2 plus and as calcium carbonate and of magnesium as magnesium hydroxide precludes the titration at such high pH. Instead, the titration can be carried out at pH 10. At this pH, a portion of the EDTA is in the HY3 form, and the additional complexation reactions and conditional formation constant at this pH are calcium ions react with the HY3 forming a complex. The Kf value is 1.8 multiplied by 10 to the power 10 when it bounds to the calcium ion, and 1.7 multiplied by 10 to the power 8 when it bounds to magnesium ion. As the EDTA and its metal ion complexes are colorless, a metal ion indicator that undergoes a color change when transformed from the metal ion bound to the unbound form is needed. Both echrom black tea and calmagite are often used in the water hardness determination. Calmagite, as we have already discussed, in its free acidic state and is denoted as H3 ion, which means the indicator. Was chosen for this determination because it provides a sharper endpoint and has a longer shelf life than echrom black tea. Concept involved in this complexometric titration, EDTA is widely used in analytical chemistry as it forms strong one-to-one complexes with most metal ions. As the EDTA titrant is added to hot water sample, free magnesium calcium ions are captured first. After complexation of all the free ions, EDTA reacts with small amount of bound metal ion indicator complex. The metal ions are effectively removed from the indicator as the EDTA binds more tightly. As we have already discussed, the Kf value of EDTA is much stronger than calmagite. This victory in the competition for the metal ion is only possible because the value for the formation of magnesium calmagite complex is less than that of magnesium EDTA complex. Because the indicator binds too weakly to the calcium ions to provide a sharp endpoint, a very small amount of disodium magnesium EDTA reagent is added to a sample to ensure a distinct color transition. The color change observed at the end of the titration corresponds to the following reaction with the EDTA in the H/3 form. In the procedure, a small amount of indicator is added to the hard water sample, and the wine red color of the magnesium indicator complex is seen initially as a small amount of magnesium becomes complex by the indicator. When the endpoint is reached, the blue color of the unbound indicator signals the endpoint of the titration, as all the ions, including those originally bound to the indicator, have been effectively complexed by the more powerful ligand EDTA because it has higher Kf value, which is the complex formation constant. The procedure that is going to be followed in the lab: place 25 ml of hard water sample in 125 ml beaker on the overhead projector. Add 1 ml of pH 10 buffer solution. Then add 10 drops of disodium magnesium EDTA reagent and 12 drops of freshly made calmagite indicator solution and stir. The solution should be wine rose color at this point. If the titration is used to demonstrate the relative values of formation equilibrium constant, add the first 20 ml of EDTA solution with graduated cylinder. The red wine color should persist. Approach the endpoint by slowly adding the last approximately 5 ml of EDTA solution with the eyedropper while stirring. As discussed above, the color of the solution will change to blue at the endpoint. The color becomes blue because the indicator is now free of the metal ions, and those metal ions are now captured by the EDTA added, as EDTA has higher Kf value. Cycle about the end point by alternating adding more hard water and more EDTA titrate. A blank with distilled water in a second beaker could also be simultaneously titrated to contrast and attenuate the effect. If the demonstration is used to highlight the applicability of complexometric titrations in quantitative analysis, the 25 ml of the hard water sample should be made with a 25 milliliter transfer pipette, and the EDTA solution should be added from a burette. Preparation of solutions: hard water sample. A hard water sample that mimics very hard water with approximately 1000 ppm chlorine may be prepared by creating a salinity of 0.25 grams of anhydrous calcium carbonate with a 3-4 milliliter of deionized water. Add 6 moles HCl a few drops at a time until the calcium carbonate has dissolved. Do not add more than 3 ml of HCl in this step. Dilute to 250 ml with deionized water. The resulting concentration of the solution is 1 milligram calcium carbonate per milliliter pH 10 buffer. Dissolve 64 grams of NS4Cl in ammonium chloride in 200 ml of distilled water. Add 570 ml of concentrated ammonia and dilute to 1 liter with distilled water. Calmagite indicator. Dissolve 0.5 grams of calmagite in 1 liter of distilled water. Still the solution for 1 hour and let sit overnight. In spite of its long shelf life, the indicator should be prepared fresh every month. The shelf life of calmagite is way higher than that of Ecodon black tea. That's why it is better when it comes to doing complexometric titrations. EDTA titrant. A solution approximately 0.010 mole of EDTA may be prepared by weighing between 0.9 and 1 gram of disodium salt dihydrate of EDTA. Place this amount into a 500 milliliter flask and add 250 milliliter of deionized water to dissolve. Sodium magnesium EDTA reagent weigh out 39.4 grams of sodium magnesium EDTA and add 750 ml deionized water. Add 15 ml of concentrated ammonium hydroxide and 10 drops of calmagite indicator. Add small portions of sodium EDTA salt until the solution is almost blue. Dilute to 1000 ml with deionized water. So that was all for the presentation. I hope you like it. Thank you.